So let's start.
Okay.
So I want just to introduce Professor Antoine Kahn, and native of France, but his whole career specifically, and even the PhD from Princeton University, right?
Yes.
So he's Professor Electrical and Computer Engineering at Princeton, and he's going to talk to us about a very interesting topic, organic electronics. So Antoine, the thing we are looking for here is to have an understanding of the way of the land, what's in there, what specifically you have done in research that is so exciting, and where you think the future is going on this field. This is this will give us kind of the roadmap for the future. So I don't want to delay anymore. And thank you for participating on behalf of IVS. And I'm very happy to just listen to your talk.
Well, thank you very much. Thank you, Sydney and Daniel and Tatiana and Gilbert and Chaim for this invitation. It's a pleasure to at least be there on Zoom. I would much prefer to be in Israel, and I hope to be there this summer if everything goes well. And I am very thankful to all of you for being there after probably a couple of very difficult nights and the day and so on. And I just hope for the best for everybody. So I'm going to talk about organic electronics, motivation, status, and promises. I will give a very general view of the field as I see it. Organic electronics is quite vast, and 1 hour is certainly not sufficient to cover everything. I will not touch much about what we have done. Some of it, we have worked on organic electronics now for 20 years or so we've done a lot, but I wanted to give a very general overview of where we are. So organic electronics, for those of you who are not familiar with the field, is a field of material science concerning the design, synthesis, characterization, and application of organic molecules, organic carbon-based small molecules, polymers, and so on and so on. And when these molecules present interesting electronic properties similar to those of semiconductors, as you will see. And you know, the whole field of organic electronics is one of thin film technology for opto-electronics, light emission, light harvesting, large area, and flexible electronics. So you know, again, what does it cover? Today, organic electronics covers light emission, lighting, and examples are here, and I will talk, of course, much more about that. And all this is based on light emitting, the light emitting diode that I will describe. Light harvesting, of course, for photovoltaic applications. And this is starting to be more than just a laboratory device. There is some applications, mainstream applications of organic photovoltaics. Flexible large area electronics also with based on the field effect transistor, organic field effect transistor, with all kinds of applications that I will talk also about, and then sensing, biointerfaces, photodetectors, and so on. So you know, it's a very broad field which is based on these organic semiconductors. So I'll talk a little bit about organic semiconductors and, you know, quasi infinite choice of materials, and especially for me the main properties that enable all these devices. Light emission, of course, with the organic light emitting diode, light harvesting with the organic photovoltaic cells. And in each of these two cases, I'll talk a little bit about some fundamental improvement that have happened along the history of organic electronics that have really pushed up the efficiencies. and then a few words about the electronics on plastics. So let's start with the organic semiconductors. So again, chemists, of course, organic synthetic chemists, for me, are magicians. They know how to assemble all these atoms and molecules together to create all kinds of materials. And here you have, just a few examples of either small molecules, such as this one, or polymers, molecules that conduct mostly holes, and molecules that are much better at conducting electrons, flat molecules, three-dimensional molecules, molecules that can be deposited in vacuum, molecules that are better processed from solution, and so on and so on. So there's a huge variety of materials, and that is, of course, one of the great attractions of the field. Now, all these materials are basically insulators, and in intrinsic state, not doped. They are essentially insulators. And when you think of organic semiconductor devices, these function always with injection of charges or extraction of charges. And therefore, one has to be able to inject electrons or inject holes in these materials. And that is depicted here, for example, where these blocks here correspond to, if you want, the valence band maximum and the conduction band minimum, called in this, for these materials, highest occupied molecular orbital, lowest unoccupied molecular orbital of different materials put together. And I'll come back to the structure of such a device a bit later. But as you can see, to make this device here, which is an organic light emitting diode function, you have to inject electrons from one side, inject holes from the other side. They recombine somewhere, hopefully in the emissive layer, and produce light. So the importance of these frontier orbitals, or these LUMOs and HOMOs, and their position in energy is paramount. And therefore, one has to understand and study that. So, these are all, of course, conjugated systems. The saturated organic molecules have much too large of a gap to be interesting, and they are essentially insulators. But these conjugated systems, like the benzene rings, are characterized by connected pi orbitals, and the electrons are delocalized over at least part of the molecule. This delocalization increases the stability of the molecule and lower the overall energy levels of the molecule. So we end up with a general picture, either for small molecules or polymers, of materials with the equivalent of the conduction band and the valence band, called, again, LUMO and HOMO, lowest unoccupied, highest occupied molecular orbital, with an energy gap in between. And this energy gap is typically, for these materials, of the order of 1.5 to 2.5 electron volts or so. And that is, of course, one of the prime interests of these materials. Now, one note of caution here, when we talk about the gap of these materials, Jean-Luc Breda wrote a very nice little paper a few years ago called Mind the Gap, to remind people that you have to really be careful about what you're talking about when you're talking about the energy gap. And if you look at the inorganic semiconductors, silicon, gallium arsenide, and even three-dimensional perovskites these days, the exciton binding energy in these materials is very low, a few millivolts or so. And therefore, when you excite an electron across the band gap with a photon, you can, even at room temperature, the electron and the hole separate almost immediately and become free electrons and free holes. And that is a measure of the single particle gap. But given that the exciton binding energy is so low, the optical gap, or the energy necessary to create this exciton, because you start with an exciton, is essentially equal to the single particle gap. Very different in organic semiconductors, where carriers are much more localized, and therefore an exciton formed on a molecule, a microexciton, will have a large binding energy of the order of half an electron volt up to 1 electron volt or so, which makes the optical band gap significantly different and smaller than the transport gap, than the single particle gap. So one has to be careful about that. And in the literature, one often sees measurements, optical measurements of a material, of an organic materials, and people take then this optical gap as the transport gap, and that is that can be quite wrong. Okay. So one has to go and measure these, and they are typically measured with either ultraviolet photoemission spectroscopy that looks at the occupied state, or inverse photoemission spectroscopy that looks at the empty states, and that leads to a complete picture of the density of state in the valence state, or the highest occupied molecular orbital, and lower level, the band gap, and then the unoccupied states, density of states up there. Okay. So here is an example of a measurement that we did quite a few years ago on this molecule, on the film of this molecule, zinc phthalocyanine, where you can see on the left here the molecular level, occupied molecular level, obtained by ultraviolet photoemission spectroscopy. So this is the highest occupied molecular orbital. And on the other side, the unoccupied molecular state with the lowest unoccupied molecular orbital. So out of all this, you can get, and other measurements that I will not go in the detail here, to measure where the position of the vacuum level, you can get a pretty full picture of the electronic structure of the film of the molecule. We're here with the highest occupied molecular orbital, lowest unoccupied molecular orbital, the electron affinity, which is the energy difference between the vacuum level and the LUMO, and the ionization energy, which is the energy difference between the vacuum level and the HOMO level. So we measure these things on a day-to-day level. And I'll come back to that in a few minutes. But I wanted to give you here what I think are the key enabling properties of organic semiconductors that have allowed the development of organic electronics. First of all, again, this unlimited choice of organic materials. And then, of course, chemistry can control the molecular structure, it can control the energy levels, photon absorption, emission, charge carrier transport, and so on and so on. So there's a huge playground of material. The other one is processability. All these molecules are deposited either via vacuum evaporation or from solution, especially for polymers, essentially near room temperature. And room temperature allows you, and that is extremely important, the use of ultra-thin, flexible plastic substrate. And that, of course, is what leads to flexible electronic that is so important these days. So ultra-thin, because of the room temperature processability, you can use very flexible substrate. The other one, and that is perhaps for me one of the most important, is the ability to stack and mix materials. And I will explain that a bit better. The fact that we do not have covalent or partially covalent bond between atoms in the lattice like in silicon, but we have here van der Waals bond between molecules. There is really very little constraint on lattice matching when you put material B on materials A. There's no thermal budget. So there is unmatched flexibility in device engineering, as I will show you in a second. And then finally, of course, the remarkable opto-electronic characteristics, very strong photoemission, very strong absorption, and therefore very good conditions for LEDs, for solar cells, for photodetectors, and so on. So let me just again go back to the unlimited choice of organic, and I showed you a couple minutes ago how to measure the highest occupied and lowest unoccupied molecular orbital. This is just a spread of various molecules we have looked at over the years. What are we looking at here? We're looking at the highest occupied molecular orbital, or the valence band of these materials, in blue, and in red at the lowest unoccupied molecular orbital. And in between, you have the energy gap. So you can see that some of these have huge gaps of 3 or 4 or more electron volts, some of them much smaller. But also you have an enormous range of ionization energies from 8.5 or more electron volt down to 2. And the same thing, of course, for the electron affinity. So some of these molecules will eventually play the role of very good electron donors for doping the material, or electron acceptors. So for n-doping the material, or electron acceptor for p-doping of the material. But I just wanted to show you this slide here, which shows again the enormous flexibility of the material parameters and the material space that we have here. The ability to stack and mix. Let me explain. Here you have a conceptual interface between 2 inorganic semiconductors. And if you want to put gallium arsenide on silicon or whatever, they do not have the same lattice constant. They do not have the same thermal budget when you grow them, and therefore at the interface, you will undoubtedly have defects and dangling bonds, broken bonds, and so on. And these are known to induce electronic states in the band gap of semiconductors. And that leads to what is called Fermi level pinning. These are recombination centers. It's generally pretty bad for electronic devices. So it's very, very difficult to grow one organic material, one inorganic semiconductor on top of another different one without this type of defect. On the other hand, as I said before, the molecules that we're talking about are closed shell molecules, and they are held together in a film by van der Waals bonds. There's no dangling bonds, and therefore when you have a film of these molecules and you want to put another film of these molecules on top, you do not create the type of dangling bonds, broken bonds that introduce electronic states in the band gap of the material. And that allows you to put things like ALQ3 on BCP, on CBP, on ERPZ, on alpha NPD without creating these types of problems. And that is a huge enabler, in a sense, to create the type of devices that I will talk about in a few minutes. Here is an example. Here's an example of a light-emitting diode, which is right here. And again, this represents the conduction band and valence band of these materials. And in this material, which is, so this is the corresponding device. And never mind what these molecules are at this point. You inject holes and you inject electrons. And in this, what you want is a recombination of electron and holes in this electroluminescent layer. So electrons come in and holes come in, and yes, you do have some recombination here, but you also have recombination in this layer because the electron, there's really no good barrier for electron here. An electron penetrates this HTL, this layer. And that leads to an undesired double emission peak. You do not want this peak. You want really only this one which comes from this electroluminescent layer. So what do you do? Because you can insert, without creating defect, you can insert another material. You insert this IRPPZ material, which has a very high LUMO, which creates a block for electrons. Electrons cannot go over this barrier, and therefore all the recombination happens in this EL. And that cleans up considerably the spectrum of emission. And that's what I need by the power of mixing and stacking. And that is unique to organic semiconductors. So let me talk, I'm going to talk now about the three parts: the light emission, light harvesting, and electronic on plastic. And light emission, of course, is starting with the OLED, the organic light emitting diodes. Everything started, the modern organic light emitting diode started in 1987 and was, in a sense, invented by Chin Tang. His picture is right here. And he actually, in 2011, got the Wolf Prize in chemistry in Israel for that. You can see that the original paper has a fairly decent citation level of 12,000 and some. This is the first viable organic light emitting diode, which then, of course, evolved into something much more complicated. But basically here, this magnesium silver contact injects electron in this ALQ3, which is a green emissive layer, and holes are injected from indium tin oxide into this whole transport layer, alpha and PD, and then recombination occurs in ALQ3 and giving you this green light. Now, things, of course, have evolved considerably. The first device had rather low efficiency. And over the years, things have evolved with a number of layers inserted to block electrons, as I showed you before, on one side, block holes on the other side, and of course develop high efficiency red, green, and blue emitters, and so on and so on. I would like to insist in particular on a fundamental improvement in the internal quantum efficiency of these devices that occurred in the late 80s, early 90s. The problem was the following. When you look at, so you're injecting electrons and holes, and when you look at the efficiency of the device, this external quantum efficiency is the product of internal quantum efficiency times the outcoupling efficiency. Outcoupling is a real difficult problem. You have to, you produce a lot of light in the device, but you really have to get it out, otherwise it's of no use. But looking back at this part here, the internal quantum efficiency has a spin formation ratio and of course the quantum yield of the molecule. Let's look at the spin formation ratio, and the problem here is that when you inject electrons and holes from the two sides of the two contacts of molecule, you have a random formation of singlets and triplet excitons due to the pairing of these uncorrelated carriers. And statistically, you only have 25% of singlet exciton and 75% of triplet exciton. And that, of course, limits considerably the efficiency of the device, because only the 25% of exciton can give you light. So in 1990, I'm sorry, it's late 1990s, the group of Steve Forrest here at Princeton University came up with the idea of introducing in the material these phosphorescent dopant. And these phosphorescent dopant each have a heavy metal atom. Here it's iridium, here also it's iridium, but platinum, ruthenium, rhenium, and so on. And the spin orbit coupling induced by these heavy atoms then promotes a singlet triplet mixing, which then allows you to essentially use these 75% of triplet exciton. And then you get essentially 100% energy transfer in the system. So this paper in 1988 was extremely important for the future development of efficient OLED. And that was the development of these PHOLEDs, or phosphorescent organic light emitting diodes, that are being used everywhere today. So if you I just pulled some statistics on lifetime, because that's also very important for applications. If you look at fluorescent OLED, the ones without these phosphor, this is the time to 50% reduction in efficiency. For the red is 160,000 hours, green 200,000 hours, and 11,000 hours for blue. Blue is always difficult because, of course, the bandgap is larger, energies involved are larger, and that leads to faster degradation. For the PHOLEDs, even considerable improvement for the red and green, not the blue, and therefore most of the applications use PHOLEDs, green and red, and fluorescent blue. But as you can see, the lifetimes of these things are now considerable, and that is, of course, very good news for applications such as displays and others. Another very interesting fundamental development happened, and a bit later, 2010 or 12, that looked at the same problem of spin ratio. And that is the introduction of molecules. If we look at this picture here, this is the ground state S0, this is the singlet S1, and this is the triplet. And these molecules were conceived and synthesized in order to have a triplet energy very close to the singlet energy. And that occurs when one of the criteria here is that the wave functions corresponding to the HOMO and to the LUMO really do not overlap at all, or much at all, on the molecule. And that, of course, leads to, given that these triplets here are non-radiative and they stick around for these quite a while, that allows to promote an efficient reconversion or spin-up conversion from the non-radiative triplet to the radiative singlet. And therefore, again, you recover most of the triplet and you get a very efficient OLED. So this is what is called thermally activated delayed fluorescence, as it goes back to fluorescence after that. So this is another very important aspect of OLED these days. So yeah, where are we with OLEDs? OLEDs, I think OLED displays are here to stay. These are very mature technologies now. Of course, the very large television that you may have seen. Of course, most of you have OLEDs in your pockets, on your cell phone. And then, of course, you have these flexible applications that are coming. Well, this is just a large display in Korea, and so on and so on. So they are here to stay. There's no doubt about that. And if you look at the market over the next few years, it's quite considerable. The cell phone displays in cell phones up to $40 billion. The dark green here are the televisions, and so on. So it's really increasing steadily. And another interesting thing is the substrate. In blue here, you have the glass-based substrate, and this is where we are now, 40% or so, and in 2030 will be down to 15% or so, which means that the flexible and the plastic substrate are going to take over on all these applications. Lighting, of course, if you have red, green, and blue, of course, you can make white light. And you all know that LEDs and solid state lighting is saving a lot of energy, and it's expected to be about 86% of installation in 2035 or so, at least in the US, and that will save a lot of energy, a lot of money eventually. The applications that we're looking at here are these OLED or white OLED applications for large panels, and that can be done in many different ways. And these are only two ways that come out of these two papers. One is where you put the three phosphors, the red and the green and the blue, in a single large band gap host, and electrons find, electrons and holes, of course, find their ways to these different molecules and so on. And so here you would have the blue and the green and the red, and these are the molecules involved. And another configuration, of course, is the triple phosphor, triple host, where the blue is in one material and the green another and the red in another. And of course, the technology and the design is quite complicated. You have to have exactly the right thickness and the right density of these phosphor molecules in there, but they are getting very, very good at that. So, the applications, again, are here. These are flexible, and these are more design type light. I've had one on my desk, and it's really very nice, warm light, which I like very much. I don't know what the future is for these applications, but it's certainly very, very appealing. Let's go over that. These are just lifetimes and so on of these materials. Let's talk about light harvesting and the organic photovoltaic cell, which is the second key application of these organic semiconductors. And again, the initiator here is Chen Tang. And actually, this paper came out a year or two before the OLED. There's a whole story about that, apparently. But and again, this is fairly decent citation levels for a paper. So this was a rather simple cell, as you will see from the evolution, with two materials, this copper phthalocyanine and this PTCBI, these two molecules, and I will explain why. As you can see, the efficiency of the device was just slightly below 1%, so at the time, not great, but it has evolved considerably since, as you probably know. So what is the main problem with organic solar cell? If we go back to the inorganic semiconductor, you absorb light, you create an exciton, and this exciton is typically a Vanier type exciton, large radius exciton, in a material that has a relatively large dielectric constant. The binding energy of the exciton is small, 10 millivolts or so. The radius is large, and if I look at this very simplistic energy diagram of the device on the illumination, you have of course electron and holes generated in the depletion region, and then they immediately are separated by the field, and also in the neutral region. And if a minority carrier like this one happens to diffuse to the interface and this one here, then you collect them also. But the dissociation of the electron is at room temperature essentially instantaneous. Organic material, the situation is more complicated. As I said before, the exciton is a Frankel exciton, small radius exciton, with a large binding energy of an EV or so. So a field like this one cannot separate, dissociate the two. And it requires the use of two organic materials arranged like this one, where this one, which will be called the donor, has a HOMO level and LUMO level higher than the HOMO level and the LUMO level of the acceptor. So the various events that take place here. Here you have absorption of a photon, creation of an exciton, and these excitons may or may not diffuse to the interface between the donor and the acceptor. So there is light absorption, there's exciton diffusion, and each, of course, have their own probability depending on the structure and so on. At this interface, if the exciton gets to the interface, there is a chance that the electron will be transferred to the lower energy LUMO on the acceptor, and eventually the electron and the hole then go their own ways and are collected, the hole to the left and the electron to the right. The exciton diffusion probability is a big issue, and it's certainly not 100% or so, nor is the dissociation of the electron and the hole once you form this charge transfer exciton. This step here is important, although this is a very simplistic way to look at it, and you should look at the physics of the dissociation of the charge transfer exciton through a excitonic state process. And of course, the energy difference between the LUMO of the acceptor and the HOMO of the donor is also very important, because eventually it limits the open circuit voltage that you can get out of this material. So this being considered, one big step that occurred many years ago was to go from the single interface device, where you have the donor on top of which you put the acceptor, to a bulk heterojunction. Why do you do that? I mean, if you look at this structure here, of course, you have more control on the structure and maybe on the mobility of the material. It's somewhat simpler, and eventually you can dope the materials. The trade-off here is that you have the trade-off between the thickness and the exciton diffusion length. If you have too thick of the material, the excitons will not diffuse all the way to the interface, and you will lose most of them. If you have too thin of a film, then you will not absorb all the light that you should absorb, and therefore, a balance. And this balance people have tried to offset this balance by then generating these what is called bulk heterojunctions, where the two are mixed. Of course, that increases the interface area between the two materials, and it shortens considerably the exciton diffusion path. If an exciton is created right here, it only has to go a short distance to this interface. The difficulty is that it is much more difficult to control the internal structure of the two, the connectivity, the conduction path, and so on and so on. So that leads to a lot of optimization and so on, which from a scientific point of view may not be very interesting, but from a technological point of view are very, very important. Typical OPV materials, the whole range of donor materials, and this is just a few of them. Acceptor materials, and acceptor materials since the beginning have been really dominated by fullerenes, and in particular by PCBM, these derivative of C60 and even C70 or so, which can be deposited by from solution. That's where okay. So this is the anatomy of a typical organic photovoltaic cell. I'm sorry, yeah, where you have a substrate, and your substrate could be a flexible plastic substrate, then a transparent contact, typically a conducting oxide, ITO or others, and then you have buffer layers 1 and 2, which have various roles, and in particular to block electrons from going in the hallway and the holes from going the electron way. So these are carrier specific materials. And then of course the OPV layer, the active layer, and then the top contact. But I wanted to come back to this issue here, I'm sorry, of the following. In 2015 or so, we started hearing from China of the synthesis and development of a class of very efficient non-fullerene acceptors, NFAs, these NFAs here, and in particular this ITIC and ITCCs and so on. Never mind what their long names is about. And these show stronger absorption in the visible than the fullerenes, and therefore you can get absorption not only in the donor but also in the acceptor. So more active participation in the current generation, and a much easier, much more possibility to adjust the energy levels of these molecules to fit them much better to what is needed with the donor that you are using. And also better stability of film morphology in these bulk heterojunction. And that led to as I say here, a rebirth of the OPV field, because for many years, up to 2012, 2013, 2014 or so, organic photovoltaic cells were stuck at about 11 or 12% efficiency, and that was really not sufficient to incite more more research and also applications for photovoltaics. Here is the famous NREL, yearly NREL solar cell efficiency plot that shows efficiencies versus time for all kinds of for technology. So it goes from the double or triple solar cell based on gallium arsenide that goes on satellite, all the way to silicon in blue, to organics in red. And as you can see, organics started, well, they started way down here, but efficiency were terrible. And then between 2010 and 2015 or so, there was really a plateau and people were getting discouraged until these non-fullerene acceptors arrived. And that led to this very significant rise up to these days about 18% or so, which is very nice. And there is really a rebirth of the field. Of course, in the meantime, the efficiencies have been overcome by perovskite solar cells or so, which are now around 26 or 27% or so. So the jury is still out on what will happen with organic photovoltaics, but it's certainly a fundamental improvement over the last few years. And here are applications. So these are the early applications, but now applications, going from niche application to some mainstream applications where you start seeing from Heliotech, for example, fairly large demonstration panels of organic photovoltaic cells in many different places. Let me spend the last 5 minutes or so on electronics on plastics. So these are based, of course, on the field effect transistor. So for those of you who are familiar with the regular, MOSFET or metal oxide field effect transistors, silicon or whatever, the structure here is not completely different. Although, of course, the MOSFET works in inversion and in deep inversion, whereas most of these organic field effect transistors function in accumulation. So here are, the three typical structure of these OFETs, either bottom gate or bottom contact. So what do we have here? We have the substrate, we have the gate, metal gate, a dielectric, the organic semiconductor in green, and the drain and the source metals. And you can have either bottom gate, bottom contact, top gate, bottom contact, and bottom gate, top contacts, all have their pluses and minuses. But basically, you put a bias on the gate. Here, for example, for a p-channel conduction, a negative voltage on the gate until you get accumulation between the drain and the source. Holes are stuck essentially at the interface between the organic semiconductor and the dielectric, and here is the same, and here is the same. So yeah, this is another representation, if you want, of the bands, HOMO and LUMO level between the source and the drain when you have a bias on the source. And these things, of course, work quite well. There have been a lot of development over the years, in particular in the crystallization as much as possible of the semiconductor to increase mobility and so on. But you get, the familiar family of curve for these devices and so on. And this is, Hagen Klauk in Germany is one of the experts in these very, very thin and rather high performance thin film organic field effect transistors. So, the best electron mobilities are, in the 5 or 10 or even 15 centimeters square per volt second. So we're not competing with silicon and other technologies, but it's very good for the type of application we are talking about here. Polymer is a little lower. They can be solution processed or vacuum processed. Flexible substrate, of course, for the same reason as before, and the lifetimes are quite good. And some researchers are now making fairly large circuits with, several hundreds of thousands of OFETs printed and so on. So here are, different molecules. Pantacene 60-DNTT can be vacuum deposited. Whole transport material, these are solution deposited whole transport materials, and these are electron transport materials, either vacuum deposited or solution processed and so on and so on. Again, showing you the vast array of materials available for these things. And applications, and these are all coming from the website and lab of Professor Takao Someya. And if you are interested, just go and look at what they've done. He's just a remarkable technologist that is pushing the field in an incredible way right now, especially toward application in wearable healthcare monitoring systems, which are all over the news these days. It's quite impressive, and these things are printed or deposited on ultra thin plastic sheets of below 1 micron and so on. So it's quite fascinating what they can do. So with this, I will finish. I think again there's a pretty bright future for organic electronics. Certainly in displays, it's a mature technology. I'm sure there will be more development, but it is quite impressive. If you have seen these very large OLED TV, 80-inch across and so on, it's just remarkable. What 30 years of high-level research has done there. Photovoltaic cells, very strong improvement over the past 5 years, I would say. And I think that 20% efficiency is certainly not out of question. And with that, there will be some applications, I think, which may require flexible or different type of structures. And I think that also plastic, electronics on plastic has a bright future as well. So I'll leave it at there, and I hope you enjoyed that, and I'd be happy to answer questions.
Thank you, Antoine. Riveting presentation. It's interesting, the index of how interesting the presentation is to see how many people drop as the presentation goes on. And I can tell you we're amazing. Steady state 70 until 5 minutes ago, and now we're over 60. So now questions. Anybody has questions for Antoine?
Yeah, if I could, Antoine.
Sure.
It's Sydney. Hi. Yeah, thank you. I really enjoyed that. I noticed that you showed a few times some data about lifetime of these LEDs. And I'm just wondering, I mean, this isn't, I guess, usually organic LEDs, but, I find myself often going to a store and buying a LED, and you see it says nicely on the box, whatever, 10,000 hours, whatever, and you make a calculation, figure it's going to last longer than the lifetime of your house. And then you're disappointed to find 2 years after that you're replacing it. Now, as an engineer, why do these things fail earlier than they should?
My honest answer is that I have no clue.
Okay.
Why do they fail? I mean, are these devices that are used, on a continuous basis? You turn it on and never turn it off, or I don't know. I don't know if they tell you 40,000 hours and it fails after 1,000 hours. Obviously, there is a problem with the manufacturing and so on, and the yield. So I don't know. I pulled out these data because I find them interesting. I'm certainly not an expert in that. So I'm not sure I have a good answer to you, other than the manufacturer is not being straightforward with the customer.
Yeah. Well, I guess if anyone had a good answer, then it wouldn't be happening. So probably there isn't a good one yet.
There's someone suggested encapsulation issues.
Yeah, I mean, there's a lot of issue that can crop up. But if they tell you, 40,000 hours and it fails after 2,000 hours, something is wrong. So yeah, it could be encapsulation. I think that the report I've read on televisions, in particular OLED televisions, have been quite good, and I don't think that people have seen much failures. You have a gazillion pixels on there, and you may have a few pixels going dark here and there, but I don't think that you can actually notice it.
Some other questions?
Yes, can I ask a question?
Oh,
Hagai.
Okay, Hagai. Then Reshef, I saw you wanted to ask a question. I have one also. The guy first.
Antoine, can you say something about thicknesses, the active layer, let's say in the PV or the in the light emission, whether or how far is it from the optimal or theoretically optimal?
I mean, so it's a complicated issue in the sense that when you have something, so you have here 20 nanometers, 10 nanometers, and so these are extremely thin. Okay, but you got to be very careful about the optical interference throughout the device in order not to distort the color that you're going to get. So it's all, you have all kinds of calculations that you can do, that optical optical cavities and so on that can be done on these materials. You need to know the dielectric constant of the materials and all these good things. Okay.
But if you want to go thinner and thinner, are there limitations that really disturb from getting to the?
Yeah, I mean, thinner and thinner at one point, it's an issue of continuity of the films or pinholes in the films that lead to leakages and so on, and eventually degradation and death of the device. So again, I gave you a 1 hour shortcut of 30 years of research, and there's a lot of just technology development and try of various things and so on that have been done. But it's mostly optical cavity. It's mostly necessary film thickness to avoid pinholes and degradation and stuff like that. Okay, and for the photovoltaic cell, it's the same, and so on. Okay, but these are very, very thin devices. Okay, we're talking about you can sum up here.
Reshef,
Antoine, thank you very, very much for this enlightening and interesting or comprehensive talk. I have one question. I heard a remark that organic solar cells pay themselves in the terms of sustainability so that you can pay off the energy within a very short time, because the production, the energy required to produce these solar cells is so much lower than the one you need for silicon solar cells or gallium arsenide based cells. Perhaps not the perovskites, but we compare the inorganic materials which are processed at elevated temperatures and organic materials which are processed at low temperatures and deposited in solution, that makes a huge difference, isn't it?
Yeah, I think so. Again, you process all these things at temperatures, either room temperature or up to maybe 80 or 100 degrees C or so. So in terms of energy, that is very appreciable. It's difficult to know what the cost of the material itself and the cost and the energy cost of the production of the materials, the synthesis of the material and so on may be. So I do not know. But yeah, I wouldn't be surprised if you can produce these things with significantly lower energy. Yeah, I don't have the numbers on that, really not. I think that also in terms of consumption, electrical consumption and so on, they are significantly lower than other technologies. The efficiency of light emission, for example, in these materials is remarkable. And A big issue in these OLEDs is, which I just mentioned it, but I certainly did not talk about it, is all the technology that you need to extract this light out, the outcoupling of the light, and with structures on top of the on top of the substrates and so on. That is also something very important in order to increase the external quantum efficiency of these things.
Antoine, I had a question for you. I've come from the synthesis, not at all on this thing, so I'm not an expert. If I say something wrong, you forgive.
And I'm not an expert in synthesis either. So.
Okay, no, one question. I assume that this comes from drop casting or spray pyrolysis from liquid solutions or something like this to do those films?
These films come, you mean these?
Yeah, you just spray, I guess, you have your solution, you get those thin layers, correct?
Well, in a device like this one, this would be done essentially by vacuum evaporation.
Vacuum evaporation.
It would be very, very difficult to do a solution deposition.
I see.
You would have to have orthogonal solvent for every single layer.
I see. Okay. Because my question was really going towards 2 points. One, adhesion between those layers, because it's only van der Waals. And the second is, at least in the world of graphene, there is this new thing, the magic angle, that when you have 2 layers that have a certain angle between the two, you can have different properties. Here, do you care about the angle?
You mean the angle?
The orientation between 2 layers.
In the plane?
Right.
Not that I know of. Most of these layers are amorphous, and actually, technologies prefer amorphous layers in general because they evolve less with time and with temperature. They're more stable, and therefore, this orientation here, I don't think is in any way relevant.
Right. Okay, thank you. Other questions? I saw there was one, Antoine, if you look at your chat.
Yeah, I can answer. Actually, I wrote the question, but I can also ask it if you allow me.
Okay, ask.
Hi, thank you very much. My question is, why the HOMO and LUMO levels are determined by UPS and IPS instead of using, for example, cyclic voltammetry? Then we can get rid of, you mentioned the exciton binding energies are quite large in comparison with the inorganic semiconductors. So if we use electrochemical band gap, maybe we can find the summation of both of them. So yeah. Why do we stick with the UPS and IPS?
Well, you want to put me out of a job or what?
No, why? Why not? Like, I'm just...
No. Just kidding. No, CV, cyclic voltammetry is another way to get to these energies. The problem is that cyclic voltammetry is going to give you the position or the oxidation and reduction potential of these molecules in the environment of a solvent, for example. And that is going to be different than the same thing for the molecule in its thin film condensed phase environment. So there are papers, and I can send you these papers if you want, that correlate CV measurement and UPS measurement and CV and IPS measurement, and they do track each other, but there's always some difference between the two. So surely CV is a good first approximation to this issue, but if you want to know what the more precise position of the HOMO and LUMO of the transport state, the whole state and the electron state in these in the thin film, then things like photoemission is probably more accurate. I hope that answers your question.
That answers. Thank you very much.
Other questions? If not, Antoine, I want to thank you on behalf of all the attendees and on behalf of IVS. Thank you very much for illuminating us on this topic. Very exciting, very interesting, and you really portrayed it in a very, very nice way. So even someone like me who has no expertise understood it. Thank you very much.
Thank you very much. Thank you to all of you who stuck around, and I hope for the best for all of you. And I hope to see some of you.
Hope to see you in person at some on-site conferences at IVS in the future once Corona will be a thing of the past.
Yeah.
Thank you very much.
Thank you. Bye, Antoine.
Bye.
Toda rabah. Thank you.
Bye.